Folks, I'm going to go ahead and get started with today. There were two handouts on this front table. One of them really is not related to today's information because it is related to naming and formulas. So what I did is I have a flow chart that kind of gives you the mental questions to ask yourself to help you go through the process of figuring out how to name a particular compound or how to generate the formula of that compound. So we've already talked about that, but I thought I'd pass out this flow chart to help you with that process since you have a test coming up. So one side is the crazier side is how to go from a formula to a name. So, you know, it asks, does it begin with metal or does it begin with ammonium? If so, then it's an ionic compound, and then you ask yourself, is that metal always, does it always have the same charge? If so, then you just name the metal when you name the anion and you're done. But if not, then you come with the Roman numeral. If it doesn't begin with a metal or ammonium, that's when you go to the other side where you'll wind up with covalent molecules. And then it asks another question of, does it begin with a hydrogen? And it continues. Now, if I recall correctly, the only thing that's not in this flow chart is the diatomic elements. On the other side, you have a flow chart that helps you go from the name to the formula. And so again, it gives you specific questions you can ask yourself to help you along the way. The other one is actually, the other handout is actually what we're going over. So I've given you the step-by-step process for developing Lewis structures. It includes in that packet, the first 2 pages are really the step-by-step and explanation on the development of Lewis structures. It also talks about the different types of groups, bonding groups and non-bonding groups. The second page, that's a periodic table. What it's showing you on this periodic table is the most common number of bonds an element has. So for example, you'll notice in the period 2 elements, carbon will always get 4 bonds, nitrogen 3, oxygen 2. And now there's always a few exceptions to the rules, but this is the most common. But what you'll notice is when you get into period 4, period 3 and beyond, you can have more bonds. And so it describes the number of bonds you can have for a particular element. Now, the next page is just your periodic table of electronegativities. You will receive this periodic table of electronegativities on the test. So you don't have to memorize the electronegativities. And finally, the last 3 pages gets into VSEPR, valence bond, bond angles, molecule polarity, and so it covers most of what we'll be discussing Thursday in the lab. So this is a handout to help you get through all of this stuff. Questions before I get started? It's a lot. I have posted this week's folder, and in this week's folder, I also posted what's going to be on the test next Thursday, so that you can start plowing through the information, because this test, folks, it is even more brutal than the last exam from the point of everything, to my knowledge. And I mean, I haven't written it, but I believe everything will either be right or it will be wrong. There will be no partial credit for any particular question. So that makes this extremely challenging. The homework is very, the homeworks I posted are similar to what you're going to see. For example, the naming, especially the mixed formulas and the mixed name one, that is going to be how it's going to appear on the test, as far as it's going to be all mixed up. The Lewis structures, they will be a question, those will be all by their little lonesome. Because for the VSCPR, valence bond, and so on and so forth, I always give you the Lewis structure to start with, so that I know you're starting off on the correct foot. And then you have to go through and give me all the information. So it's a big test coming up, and just letting you know. That way you can start studying and have a little over a week to get through it. Yes.
What all are we given for the test besides the periodic?
You'll be given the periodic table. You'll be given the periodic table of electronegativities. As of right now, you'll be given a formula sheet, because you'll have the formal charge formula on it. But I want to say that's it. I can't remember any of the rest of it without looking at what's going to be on the test. So, questions? Okay, if not, we're going to get into and focus on Lewis structures today. I started the discussion of Lewis structures on Thursday of last week. We went over some very basic Lewis structures. Today we're going to steadily get more and more difficult with our Lewis structures. So the first thing I'm going to do is Lewis structures for what I consider to be regular compounds. And then we're going to get into Lewis structures of ions, which will flow into Lewis structures that involve an expanded octet. And then we'll talk about resonance. So that is where we're headed. So let's just talk about carbon dioxide, and I will be following these step-by-steps that I gave you today to demonstrate how you can use all this stuff. So in carbon dioxide, we have one carbon atom, we have two oxygens. Carbon is in group 14, the last digit is a 4, so it has 4 valence electrons. Oxygen's in group 16, the last digit is 6, so it has 6 valence electrons. The carbon therefore contributes 4 valence electrons to the overall structure, and the oxygens contribute a total of 12 for 16 valence electrons that need to be distributed around the molecule. Step number 2 says to write the skeletal structure. Basically, what we've got to do is determine who the central atom is going to be. Now, I gave you some very specific things, but the darkened bullet point is the most important, and that is typically it's the first element listed in a formula except hydrogen. So the first element listed is going to be carbon, around which we're going to place our other elements. We then start to distribute our electrons among these atoms, giving each atom an octet except for hydrogen. So we start by drawing a single bond between each of the outer atoms of the central atom. For each bond you draw, you subtract 2. I drew 2 bonds, so 2 times 2 is 4. So I'm going to subtract out 4 due to the bonds, which will leave me 12 electrons left to distribute. It says distribute the remaining valence electrons around the external atoms, giving the external atoms an octet. So I'm going to make sure my oxygen atoms get an octet. Right now, I have 2 within the bond that the oxygen has. To give that oxygen an octet, it needs 6 additional electrons. The other oxygen will also need 6 additional electrons. So that means we've used up our 12 electrons on our external atoms. At this point, you cannot add any electrons. When you hit 0, you cannot add dots. You cannot add bonds. All you can do is manipulate what's there. So, if atoms lack an octet, then we're going to form a double or triple bond as necessary. So what we're going to do is we're going to bring in 1 pair of electrons off of the oxygen atom. In so doing, this structure arises. And you say, does everybody have an octet? Every time you manipulate your structure, you ask, does everybody have an octet? Every time you manipulate your structure, you got to ask, does everybody have their octet? The oxygen on the right has an octet because it has 4 electrons in the non-bonding pairs, and it has 4 electrons in the bonding pairs. Your oxygen on the left has an octet because it has 6 in the non-bonding pairs and 2 in the bonding pairs. But your carbon currently only has 6. It has 4 within the double bond and it has 2 within the single bond. Because not everybody has an octet, we've got to manipulate the structure still. So we're going to bring in another pair of electrons. To share. And chemistry really likes symmetry. So instead of bringing more in off of the oxygen on the right, we're going to make sure this molecule is symmetrical by bringing in some off of the left. And when you manipulate it, you ask, does everybody have an octet? The oxygen on the right still has an octet. We didn't manipulate it. So it's really the other 2 atoms that we have to ask, do they have their octet? The oxygen on the left has an octet because it has 4 in the bonding groups and it has 4 in the non-bonding groups. The carbon also has an octet because it has 4 in each of the double bonds. 4 times 2 double bonds is 8. So this is the structure for carbon dioxide. Questions? I'm trying to get our brains going. Let's look at one more that is just a general question. Let's look at hydrogen cyanide. This formula has 1 hydrogen, 1 carbon, and 1 nitrogen. Hydrogen is in group 1, the last digit of 1, so it has 1 valence electron. Carbon is in group 14, the last digit is a 4, so it has 4 valence electrons. And nitrogen is in group 15, the last digit of 5, so it has 5 valence electrons. The hydrogen contributes 1, the carbon contributes 4, and the nitrogen contributes 5, for a total of 10 valence electrons to distribute. The next thing we do is we draw our skeletal structure. Again, when drawing the skeletal structure, typically the first element listed is your central atom, unless that element is hydrogen. Hydrogen will never be the central atom. The other thing is carbon will always be the central atom. Carbon loves to be the center of attention. So the carbon is going to be the central atom around which we're going to surround it with a hydrogen and a nitrogen. Now we need to start distributing our electrons. We start by drawing a single bond between the external atoms and the central atom. For every bond you draw, you subtract 2. We drew 2 bonds. 2 times 2 is 4. So we're going to subtract out 4 due to our bonds. And that leaves us 6 valence electrons left to distribute. The next step says to distribute the remaining valence electrons around the external atoms, giving the external atoms an octet. Folks, hydrogen already has an octet because it only requires 2 to achieve its octet. So we're going to be distributing our valence electrons around our nitrogen. Currently, nitrogen has 2. To give nitrogen a total of an octet, it needs 6 more electrons. And we hit 0. When you hit 0, all you can do is manipulate what you have. You cannot create any more dots or any more bonds without manipulating what you already have. So we asked, since we're at this point, we asked, does everybody have an octet? Our hydrogen has an octet because it only requires 2. Our nitrogen does have an octet because it has 6 in the non-bonding pairs and 2 in the bonding pairs. But your carbon atom currently only has 4 because it has 2 in each of the single bonds. So no, not everybody has an octet. So we're going to have to share a pair of electrons, and the only place they can come from is the nitrogen. And when we share a pair of electrons, the structure we create is this structure. Anytime you alter the structure, you have to ask, does everybody have an octet? Your hydrogen still has an octet because it has its 2 valence electrons, which is what it needs. The nitrogen has an octet because it has 6 in the lone pairs and, it has 4 in the lone pairs and 4 in the double bond. But your carbon currently only has 6, 4 in the double bond and 2 in the single bond. So no, not everybody has an octet. So we're going to have to share another pair of electrons. And again, they're going to have to come from the nitrogen because the nitrogen's the only one that has any electrons. So you have HC triple bond N, where the nitrogen still has a lone pair. Because I altered this, I asked, does everybody have an octet? The hydrogen still has its 2. The carbon now has a total of 8 because it has 6 in the triple bond and it has 2 in the single bond for a total of 8. And our nitrogen still has 8 because it has 6 in the triple bond and 2 in the non-bonding lone pair. So this is the structure for hydrogen cyanide. Now, folks, you do not have to do every single step in the process unless it helps you do every single step in the process. You can go straight to the answer. You can do a bunch of erasing as you go. I'm writing it out so that you can see every single step in the process. Questions? Yes.
Carbon being center of attention, is that why life is carbon based?
Well, that's why I call it the center of attention, because it is, carbon is the main ingredient and the main element in anything that's living. So it loves to be the center of attention. Okay, any questions about regular molecules and the process? If not, then let's get into an ion. We're just going to start. Oh, before I do that, actually, I want you to look at the back periodic or the periodic table that's on the second page of the packet. again, if you know this, if you understand this periodic table, it's going to help you understand how many bonds something can have. You will notice that up in the left-hand corner, hydrogen can only have one bond. That's all it's ever going to have. And if you look at the structure for hydrogen cyanide, you would see that it only got one bond. If you look at carbon, which is second period, fourth one over, it will always have 4 bonds. So whether that 4 bonds comes from all single bonds, whether that 4 bonds comes from 2 double bonds, such as in carbon dioxide, or whether those bonds come from a single bond and a triple bond, it doesn't matter. Carbon's going to get 4 bonds. Oxygen prefers 2 bonds. So up here in carbon dioxide, it had 2 bonds in the form of a double bond. And finally, your nitrogen prefers 3 bonds. So notice in hydrogen cyanide how many bonds it has. It's a triple bond, because that, whether your nitrogen gets 3 bonds that are single bonds or whether it gets a triple bond, it doesn't matter. It's going to get 3 bonds somehow. Okay, the next one I'm going to do is ammonium. Ammonium is going to be one of those that doesn't fit this thing, but it's the first of the ions that I want to do, because again, it's fairly straightforward ion. So we're going to start the same way. We have 1 nitrogen and we have 4 hydrogens. Nitrogen is in group 15. The last digit is a 5, so it has 5 valence electrons. Hydrogen is in group 1, the last digit of 1, so it has 1 valence electron. So there's 5 from the nitrogen and there is 4 from the hydrogen, for a total of 9 valence electrons. Now, step number 1 in doing this, though, it says if you have a cation, you're going to subtract that number of electrons. So since I have a +1 charge, I have to subtract out 1 due to my cation. Meaning I actually only have 8 valence electrons to distribute. The nitrogen is going to be the center of attention around which we're going to place all hydrogens to develop our skeletal structure. We then distribute the electrons among the atoms, giving the atoms an octet. We're going to start by drawing a single bond between each of the outer atoms and the central atom and subtracting 2 for every bond we draw. We drew 4 bonds. 4 times 2 is 8. So we're subtracting out 8 valence electrons due to the bonds that we drew, meaning we have hit 0. What do you do when you hit 0? Find out if everybody has an octet. Hydrogen has, each of the hydrogens have 2 because they have 2 within their single bond. The nitrogen has a total of 8 because it has 4 single bonds, each containing 2, so that's a total of 8. So there is one more thing that you have to do, and this is not, I don't know if I wrote this in here. For some reason, it doesn't look like I wrote it in here. So this is something you'll need to add to the sheet. Basically, if you have an ion, you have one more step after you've gotten the basic Lewis structure. If you have an ion, you need to put the ion in brackets, just like we were doing with ionic compounds. with the charge outside the bracket. Just like in ionic compounds, you have to put the ion in brackets with the charge outside the bracket. And this is the Lewis structure for ammonium. If you have an ion, whether it's in an ionic compound or a polyatomic ion, if you have an ion, you must put the ion in brackets with the charge outside. Okay. I'm gonna save the rest of the ions for for a little bit later, because I think all of them involve resonance except hydronium. So, and we're gonna move on to the next phase. You will notice when looking at this periodic table that I gave you on the second page, for the most part, your period 2 atoms can only go up to 4. I mean, period 2 only goes up to 4 bonds, period. There's no option. It goes to 4 bonds. But when you get to period 3, you can have more than 4. You can have an expanded octet when you get to period 3. Knowing quantum numbers. This comes back to quantum numbers. Knowing your quantum numbers, why can you have an expanded octet when you get to period 3? Because you got the D. Even though in period 3, the D subshell does not get filled, it's there. It's just we don't fill it immediately. So because of the fact that you have the D subshell available, you can have an expanded octet when you get to period 3 and beyond. Now, let's look at an example of a period 3 and beyond. We're going to look at sulfur trioxide. Okay, we have 1 sulfur and we have 3 oxygens. Sulfur's in group 16, therefore it has 6 valence electrons. Oxygen is also in group 16, therefore it has 6 valence electrons. So the sulfur contributes 6, the oxygens contribute 18 for a total of 24. Now, when we draw our single bonds, or when we come up with the structure, the sulfur is going to be the central atom around which we're going to place our others. We're then going to draw a single bond between the outer atoms and the central atom and subtract 2 for each bond we drew. We drew 3 bonds. 3 times 2 is 6, so we'll subtract out 6 due to the bonds, and that leaves us 18 left to distribute. We're told to give our external atoms an octet. So we're going to give our external atoms their octet. In giving our oxygen atoms an octet, each one needed 6 additional electrons. So 6 times 3 is 18, so we have used up all 18 electrons in our outer atoms. And we have hit 0. When you hit 0, all you can do is manipulate what you already have. You cannot make new bonds without manipulation, and you cannot add dots. All you can do is manipulate. So according to our rules, we want to make check, does everybody have an octet? Our oxygens do have an octet. They have 6 within the lone pairs and 2 within the single bond. That is true for all 3 of our oxygen atoms, but our sulfur only has 6 because it only has 2 within each of the bonds. So we're going to need to bring in a pair of electrons to share. When you bring in a pair of electrons to share, the structure that emerges is this structure. And you asked, does everybody have an octet? Because we manipulated the structure. The oxygen atoms that you didn't do anything to still have an octet because they have 6 in the lone pairs and 2 in the double bond. The oxygen that you manipulated, it also still has an octet. It has 4 in the lone pairs and 4 in the double bond. And your sulfur at this point does have an octet because it has 4 in the double bond and it has 2 in each of the single bonds, giving it 4. So it has a total of 8. Now, here is where we run into an issue though. So far, we've just followed the rules, but sulfur is in period 3 or greater. So you have to ask, do I need to expand the octet? And one way to determine if you, and the way to determine if you need to expand is to calculate the formal charge on each atom. Now, if you look at page 2, step 6, you will find the equation for calculating the formal charge. You will also, on that same page, find out how to determine whether or not you have the correct structure. So the formal charge calculation is it's the number of valence electrons, and we're going to subtract out 1 for every bond that we have and 1 for every dot that is on that atom. To know whether or not you are correct, the absolute value of all of the formal charges should be equal or as close to 0 as possible. If you have to have a negative formal charge, it needs to go on the more electronegative atom. And you will never have like formal charges side by side. In other words, you're never going to have a negative next to a negative. You'll never have a positive next to a positive. So those are the 3 criteria that determine if you have the correct formal charge. Is it as close to 0 as I can get for the absolute value? If I had to have a negative, which we will on all of our polyatomic ions, nearly. If it has to have a negative, is the negative on the more electronegative atom. And then making sure that like formal charges are not on adjacent atoms. So we're going to calculate the formal charge for each of the bonds and atoms in this. So sulfur has, and I'm using the equation that I gave you. Sulfur's formal charge is equal to its number of valence electrons. It has 6 valence electrons, minus 1 for every bond. There are 4 bonds on that atom, plus 1 for every dot. There are no dots on the atom. So the formal charge for sulfur in this structure is a +2. We'll do the formal charge for each of the single bonds. They look identical, so that's why I just draw a -O to tell me it's a single bonded oxygen. Oxygen is in group 16, last digit is 6, so it has 6 valence electrons. We're going to subtract out 1 for every bond. There is 1 bond, and 1 for every dot. There are 6 dots. So the formal charge on the single bonded oxygens is a -1. So right now, this one has a -1, and this one has a -1, while the sulfur has a 2. We would be remiss if we didn't go ahead and calculate the formal charge for the double bonded oxygen. It has 6 valence electrons. We're going to subtract out 1 for every bond. It has 2 bonds and 1 for every dot. It has 4 dots for a total of 0. So the formal charge on this other one is 0. The absolute value then is +2 plus the absolute value for -1 plus the absolute value for -1 plus the absolute value for 0. In other words, I've got the absolute value is equal to, so it's 2 plus 1 plus 1 plus 0, or in other words, we have an absolute value of 4 for our current structure. That's bad. You want to minimize formal charge. You want to get it as close to 0 as possible. So because sulfur is in period 3, we know we can expand its octet. It can have more than 8. So we're going to bring in a pair of electrons to share. And when you bring in the pair of electrons, we now have sulfur double bonded oxygen. But we now have 2 double bonded oxygens. If you did not manipulate it, it's still going to have the same formal charge. So since we didn't manipulate this one, it's still a -1. Since we didn't manipulate the oxygen on the right, it's still a 0. You only need to recalculate the formal charge for the elements you manipulated. So the formal charge on our sulfur, we have 6 valence electrons minus 1 for every bond. Now we have 5 bonds plus 1 for every dot. There are still 0 dots. So we're down to a +1 formal charge on our sulfur. Our other double bonded oxygen that we made, it has 6 valence electrons minus 1 for every bond. It has 2 bonds now plus 1 for every lone electron. It has 4 of those, so it has made it to 0. So this now has a formal charge of 0. The absolute value of everything then is the absolute value of -1 plus the absolute value of a +1 plus the absolute value of 0 plus the absolute value of 0 means that our absolute value is now down to 2. So we improved it, but we're not there yet. We want to minimize the formal charge. So we're going to bring in another pair of electrons to share. And when we bring in that other pair of electrons to share, the structure that emerges is this structure. The elements we did not alter, they still have the same formal charge. So this one still has a formal charge of 0. This one has a formal charge of 0. The question is, what did we do to the other oxygen and the sulfur? So the formal charge on our sulfur is going to be equal to 6 valence electrons minus 1 for every bond. It now has 6 bonds plus 1 for every dot, so it has 0. So it now has a formal charge of 0. And the formal charge on the new double bonded oxygen is 6 valence electrons minus 1 for every bond. It has 2 bonds plus 1 for every dot. It has 4, so it has now hit 0 as well. So in other words, it adds up to 0 for the overall formal charge. So we have minimized the formal charge. So in other words, sulfur trioxide has 3 double bonded oxygens. You can look at your little chart here to see if it makes sense. Oxygen needed 2. So the fact is sharing those extra electrons just made oxygen happier. And sulfur could either have 2 or it could have 6. In this particular case, it wanted 6. So this is just a guideline to help you out here. Questions about an expanded octet, because we're about to combine it all and add one more piece. So let's look at sulfate. Sulfate combines everything you've already learned and adds one more piece. And I'll explain that piece when I get to the end. Okay, so we have 1 sulfur, we have 4 oxygens. Sulfur's in group 16, the last digit is 6, so it has 6 valence electrons. Oxygen's in group 16, the last digit is 6, so it has 6 valence electrons. The sulfur contributes 6, the oxygens contribute a total of 24 for a current total of 30 electrons. But this is a charge. It is an anion, so we're going to add the magnitude of the charge to the total. So we're going to add 2 electrons to this for the charge, for a total of 32 valence electrons to distribute. We start by determining our skeletal structure. The first element listed is typically going to be your central atom, around which you're going to place everybody else. We then start distributing those valence electrons. The first thing we need to do is we need to add single bonds between the outer atoms and the central atom. And we're going to subtract out 2 for every bond we drew. We drew 4 bonds. 4 times 2 is 8. So we're subtracting out 8 due to the bonds, leaving us 24 valence electrons still to distribute. The next step says to give all the outer atoms an octet. Our oxygens currently only have 2 valence electrons found within that single bond. So to give them an octet, we have to add 6 additional valence electrons to every single oxygen atom. So 6 additional valence electrons times 4 oxygen atoms, that is a total of 24 electrons that we put on our external atoms. And we have hit 0. When you hit 0, you ask, does everybody have an octet? And the answer to this question is yes, everybody has an octet because sulfur has 8, oxygens have 6 within the lone pair and 2 in the double bonds. 2 in the single bond. So it has 8, and that is true for all of our oxygens. So we have an octet. Unlike sulfur trioxide, we're already at an octet. But what do I have to pay attention to? Formal charge, why? Because it's sulfur's in period 3 or greater. So let's do formal charge of these things. The formal charge of my sulfur, it has 6 valence electrons minus 1 for every bond. They have 1 bond. Sulfur has 4 bonds on it and 1 for every dot. It has 0 dots. So right now this sulfur is sitting with a +2 formal charge. The oxygens are all identical, so I'm just going to do once. There are 6 valence electrons minus 1 for every bond on one of the oxygens. We're focused on one oxygen at a time here. There is 1 bond and there are 6 electrons, making the formal charge on each oxygen atom a -1. Okay, we need to minimize formal charge. So we're going to, because right now, if I were to calculate the formal charge of this, I would have a +2 absolute value plus a -1 plus a -1 plus a -1 plus a -1, meaning that I have an absolute value of -6. That's a lot of formal charge. So we're going to be sharing a pair of electrons between the outer atom and the central atom. And the structure that is going to emerge when I share that pair of electrons is this structure? If we did not change the atom, the formal charge is still the same. So this has a -1, this has a -1, this has a -1. But you'll need to calculate the atoms that you did change. So the formal charge on our sulfur is that it has 6 valence electrons, -1 for every bond. It has 5 bonds now, +1 for every lone electron. It still has none of those. So we did make it into where this is now a formal charge of a +1. And our formal charge on our double bonded oxygen, it has 6 valence electrons, -1 for every bond. It has 2 bonds, +1 for every dot. It has 4. So we made that one into a formal charge equal to 0. So if we're looking at our absolute values of everybody, we now have a total formal charge of 4. We reduced it quite a bit, but it can be reduced further. And this is where come back up to the same thing I mentioned earlier, chemistry liking symmetry. We're going to bring in a pair of electrons, but we're going to bring it in from the opposite side. So when we do so, the structure that forms is this structure. And everything that remained the same, the formal charges remain the same. So we only have to calculate it for the things that we changed. So the formal charge on our sulfur is going to be equal to 6 valence electrons -1 for every bond. It now has 6 bonds, +1 for every dot. It has none. That means we got the sulfur down to 0. And for our oxygen atom that we made, it was a double bonded oxygen. We have 6 valence electrons, -1 for every bond. It has 2 bonds and 1 for every lone electron. It has 4. So that means it also is 0. So now if we look at the absolute value of our formal charge, it would be a +1, +0, +0, +1, +0, or in other words, it's a total of 2. Now, before I go further, I want you to tell me why I would not make this structure for my sulfate ion. Why is this structure not valid? Why do I not go one step further? Huh? But why? Not quite, because period 3, I mean, if you've got D subshell, you've got the opportunity to make 5 more bonds. But why would I quit?
The formal charge for sulfur is already 0, so
I wouldn't want it to go in the opposite direction. But that doesn't, I mean, ideally, but that doesn't answer it because my oxygen I'm just made would have a 0 now. So this, I will tell you up front, this structure, whoops, come back. This structure also has a formal charge, absolute value right now of 2, just like the other one. But there's some reason why you can't have this structure.
It's not symmetrical.
Symmetry is nice, but that's not it. Calculate the formal charge on the sulfur and the oxygen you changed. I want you to calculate the formal charge on the sulfur and the oxygen I just changed. See a couple of people doing it, but not many. I want you to calculate the formal charge on the structure. And tell me why this structure cannot exist. Okay, sulfur's a -1. And what else? The new oxygen's a 0. So right now, what you're telling me is that this has a formal charge equal to 0. This one has a formal charge equal to 0. This one has a formal charge equal to 0. This one has a formal charge equal to a -1. That is the answer. If you look at the formal charge, you have a negative against a negative. What happens when you have negatives, magnets going up against a negative magnet? They repel. They break the bond. So this one is not valid because like formal charges cannot be on adjacent atoms. So even though the overall formal charge was the exact same, it can't exist. So why can't this one exist then? Okay, the like formal charges I get, but why couldn't we have this? I mean, if you look at this one and calculate the formal charge equals 0 on all of your oxygens. Isn't that awesome? Wouldn't this be awesome? I mean, because the formal charge on sulfur is a -2. We still have an absolute value of formal charge equal to 2. But why is that one bad? Oxygen is more electronegative than sulfur. So and if somebody has to have it, somebody needs the negative charge. It should be oxygen. That's part of the answer. But there's also the fact that you really want the numbers to be as close to zero as possible. So that structure really is problematic because of really two reasons. But so this one would not be valid either. So going back to what is valid. Let me see how I had it listed there. Okay. The one I had listed that was valid was this structure. And because it is an ion, you're going to place it in brackets with the charge outside. Now, there's one more part to this one though. Sulfate is a good example on everything. Why the right and left oxygen? Isn't the top oxygen and the bottom oxygen the exact same? I mean, they're all oxygens. Is there a reason I put it on the right and left? Can anyone figure out if there's a reason why I put it on the right and left oxygen instead of the top and bottom oxygen? They're all the same. I mean, if you go back to our original structure, all the oxygens looked identical. So they're all the same. So why the right and the left? Probably because I'm right-handed. And then chemistry likes symmetry. In other words, there is no reason why the right and the left. I have two other oxygens that were identical. I mean, all four oxygens were identical. And because of that, what we can develop with sulfate is what's called a resonance structure. Step 7. Page 2, draw resonance structures if they apply. Yes.
Does sulfur still have an octet even though it has 6 bonds?
It just has to have 8 minimum to have its octet. It has now a 12. I don't know what the name of that would be, but it just has to have a minimum of 8 for sulfur. For some molecules, more than one valid Lewis structure can be written. Resonance will be necessary if you make a conscious decision as to who or as to which outer atoms share a pair of electrons with the central atom, but you could have made an equivalent choice. I made a decision, it was the right and left, but I could have made an equivalent choice because they were all identical to begin with. So when resonance structures exist, you draw a double-headed arrow. And you have to draw all resonance structures. Folks, most of your polyatomic ions, if not all of them, are going to have at least one resonance structure. I mean, at least one more resonance structure. So if you see a polyatomic ion, you better ask yourself, can it have resonance? Because most likely it can. There's a few other molecules out there, but your polyatomic ions, almost all of them have resonance. So you must draw a resonance structure if they apply. So the rules to drawing resonance structures. Is to A, draw all possible forms. And it will always be done by the manipulation where the double bond or where the multiple bond is. And B, separate those structures with a double-headed arrow. What I've done today is I've introduced all of the various Lewis structures. We have followed page 1 and 2 and even looked at page 3 fairly extensively. On Thursday morning, we're going to look at just one of these little bonds at a time and talk about bond lengths and bond strengths and bond dissociation energies and talk about bond polarity. Then in lab, we're going to meet in 105 and we're going to come back to all these molecules, plus I will do more. And we're going to talk about VSEPR theory. So you will need this packet all day Thursday as well. So don't leave this packet behind because it will come in handy all day Thursday. But we'll be talking about atomic structure and we'll talk about the electronic geometry. We'll talk about the hybridization on the central atom. We'll talk about the molecular geometry. We're gonna talk about bonding angles. We're gonna talk about molecule polarity. And we're gonna talk about how to describe the bonds as well. So lots and lots of information is coming up on Thursday. If I'm not mistaken, I did. If I'm not mistaken, I did try to make sure that, and I need to look, but I want to say I stopped the test as of Thursday's information because it's such a major to do. But I'll look and I'll let you know Thursday morning. But I think I did stop the test as of Thursday's information because this is a lot. Any questions? If not, we're getting out a couple of minutes early.